Welcome everybody to our inaugural version or inaugural SURE, which we call Strategic University Research Expo, a virtual gathering. And you can imagine all the jokes we use around SURE, so for sure and all those things. But anyway, I'm Andy Wilson. I'm the Executive Director of the Alliance for SoCal Innovation. I'm your host with Jen, also known as Katie, today, who was point on putting this together. I just thought I would spend a minute on the Alliance and then kind of a little bit on where this came from, and then turn it over to Pete, who's agreed to be the ringmaster today. So for those you, once again, who aren't familiar with the Alliance, our mission at the Alliance, and we're a not-for-profit, is to more fully capitalize on SoCal's compelling diversity of talent, ideas, and perspectives by creating optimal conditions for SoCal innovators to bring more breakthroughs to the world. We're super long on SoCal. We think Southern California has incredible diversity of industries, technologies, people, research universities. It's really an incredible mosaic of innovation ingredients. And the role of the Alliance is really to serve as that super connector by helping key stakeholders kind of navigate and more effectively engage this incredible landscape to support their own innovation objectives. And so the Strategic University Research Expo, or SURE, is a perfect example of that. It's really a way for our corporate partners to see the incredible research that's going on in this rich network of universities that populate Southern California. The program was spawned from another program that we've been running for a few years called First Look, which is our fall event. We did that in September, where we curate 30 startups coming out of universities and essentially bring them to the commercial marketplace, investors, corporate researchers, so on and so forth. We moved that to a virtual format this year with great success. I was concerned about that, I have to confess, but we ended up with twice as many people participating in an incredible selection of companies. And we kind of started thinking, well, if we only do this once a year and it's really a broad array of companies, imagine the opportunity to do this on a much more highly curated basis. So SURE is really kind of the, I would say, the more regular cadence activity around providing corporate innovation leaders with access to compelling research coming out of institutions and academia, and it's thematically oriented. As I mentioned, this is our beta run, so bear with us. We think this is an incredible opportunity, and it's our first time at it. So we have, with Pete's help, carefully selected compelling research from, I see, top universities focused on VR, AR today. We looked at over 20 teams, principal investigator teams and research teams, and we're pleased to show you a few of the best of the best. I know in your agenda, they were hyperlinks to other great companies, other great research teams in the area, so I encourage you to look at those as well. And I say, this is a bit of a test drive. We have another test drive on December 15th in collaboration with Biocom, focused on oncology. For those of you who are interested in the life science area, we're happy to invite you to that as well. And we are hopeful these two beta test drives are exciting and valuable for both you as our corporate partners, but also the principal investigator teams, that this becomes something we can institutionalize on a monthly basis in 2021. So we are committed to bringing expert curators in their respective fields to help select the teams to facilitate the session. Today is no exception. We're happy to have Peter Khashoggi, if I got that right, Pete. I like the phonetic spelling. Thank you, Jen, for that. But before I introduce Pete, I thought we would just do a very quick round of introductions, just to say who your name, what organization, and what your role is, just so we know who's joined us today. Jen, we know. Andy, I know. Pete, we're going to do a more formal introduction, so I'm just going to go around the ring here quickly. I see Kyle McCullough next. Kyle, can you just introduce yourself?
Sure, thank you. Yeah, I'm Kyle McCullough, and I'm the Director of Modeling and Simulation at USC Institute for Creative Technologies. I'll be presenting our One World Terrain research today.
Excellent, Kyle. Thanks for joining us. Lisa McFadden, please.
Good morning. Sorry, I'm in the car. I am the CEO of Expo Games, and my business partner is Dr. Jacob Rosen, who will be presenting from UCLA. And we have a stroke rehabilitation VR game.
Excellent. Lisa, look forward to that.
Thank you.
Let's see. Next on my list. Hold on. Randall Hill.
I am the executive director at the Institute for Creative Technologies, part of USC, and we're an Army UARC, or University Affiliated Research Center.
Excellent. Something's happening. I see Steve. This is Steve, so I'm not sure who that is.
Yep.
There we go.
Yeah, so yeah, I'm Steve McCloskey, UCSD alumni, founder, CEO of Nanum. We create virtual reality software for designing drugs, molecules, and things to cure COVID and other diseases.
Excellent. Thanks, Steve. And I'm not sure I'm going to pronounce this right, but Josie Chen?
Yeah, hey, you can call me Jessie.
Okay, Jessie, that's a lot easier. Thank
yeah,
you.
no worries. So I'm a professor at University of California, Riverside, and I'll be presenting today in my work on mobile AR. Thank you.
Excellent. Thanks, Jessie. Clark Lethen.
Hi, I'm the Managing Director at the Institute for Creative Technology, supporting Dr. Hill and Kyle McCullough. Thank you.
Excellent. Ricky Rath.
Good morning. I'm Ricky Rath. I'm Business Development Associate at UCLA, and there's two technologies we have for you today, and I'm looking forward to watching them present.
Excellent. Looks like Theodore Albertson. Theodore, there you go.
Hi there. Sorry about that. Yeah, this is Teddy Albertson speaking. I'm an investment associate with Kairos Ventures.
Thanks for joining us, Ted.
Happy to be here.
Christopher Huff.
Hi, my name is Christopher Hoff. I'm with Southern California Edison's Grid Technology Innovation Department, where I'm currently working on various XR implementations into the utility space.
Excellent. Thanks for joining us. And Edison's a great partner of ours, so we're super excited to have you here. Amy Hurwitz.
Great, good morning. I'm a project leader at the Boston Consulting Group based in the Los Angeles office, and really happy to be here today and looking forward to the presentations.
Excellent. Rishab?
Morning, this is Rishabh. I'm part of the Boston Consulting Group venture building arm, design strategist, and a big fan of the Alliance for SoCal.
Thanks, Rishab. Thank you for the call out. Steve Gillison.
Hey everybody, Steve Gillison here. My video, there we go. The head of programs and operations at the Alliance, here to support Jen and everybody with moral support and just happy to be here.
Excellent. Andre, you're next.
Hey, good morning, everyone. This is Andre Dumont. I'm with the Aerospace Corporation here in El Segundo, federally funded research center for space technology.
Excellent, Andre. Doing great work in the aerospace industry. Let's see. Nick Griffin, I see next. Nick, you're on mute. The most popular two words in the English language these days.
Yes, of course. Hey, Nick Griffin, Executive Director of the Downtown Center Bid in downtown Los Angeles.
Excellent. Good to see you. And unfortunately, my screen has moved around a little bit, so if I miss some people, please remind me. Craig from City National. Craig, you there?
Hey, yeah, this is Craig Schleicher. I was the innovation team at City National Bank, and for today's purposes, I'm probably the dumbest guy in the room about these topics, so appreciate the remedial intros on some things. Thanks, everyone.
Don't worry, there will be a quiz afterwards. Tony Driscoll.
Love it.
Hi guys, Tony Driscoll at Warner Media.
Hey, Tony, good to see you, or good to hear you. Safir Bilali.
Hey everyone, my name is Safir. Thanks for having me, Andy and Jen. I head up digital innovation for VF Corporation and basically support, run an internal incubator and a digital innovation team supporting the 20 brands of the portfolio. Vans, North Face, Timberland, Dickies, and most recently Supreme.
Awesome, very cool stuff. Let's see, Josie Gip, did I get that right? Jess, today, are you there? See the off mute, but I do not hear them. Yes? Okay, well, we will move along. Is there anyone that I missed? Randy Hill, did I miss you?
No, you got me.
Okay, sorry, I'm gonna keep track of everyone's in motion here. Is there anyone who I did miss? I'm sorry, like it's the checkered board that's dynamically moving.
No problem. Kevin Sharp with Southern California Edison. I'm a senior manager in grid technology innovation. I work with Chris Huff, and we are interested in any kind of out of the box thinking for inspections, safety, training, anything like that. So we're really looking forward to hearing what all you have to say.
Excellent. Thanks, Kevin, for joining us. Is there anyone else that I may have missed? Okay, with that, and I know people are going to pop in and out, so bear with us. Anyway, I want to turn it over to Peter. I thought I would give a brief bio of Peter, and we're super thrilled to have someone of his credentials and knowledge leading today's session for us. Peter is the regional lead for the Army Research Lab located in Playa Vista. He's an adjunct professor at UC Santa Barbara in the Department of Psychology and Brain Sciences. As you may know, Army Research Lab, or ARL West, is California's hub for the United States Army Combat Capabilities Development Command's Corporate Research Lab, and focuses on human and information interaction research that will provide fundamental knowledge for new warfighter capabilities such as augmented reality and virtual reality interfaces and visualization. So very appropriate area of focus for him. Pete has been a principal investigator on recent projects that leverage wearable, wow, these are big words, physiological sensors for improved human autonomy teaming, as well as fundamental and applied research on training effectiveness for simulation. I probably would read that better if I had my coffee beforehand. He has over 50 peer-reviewed publications in the areas of cognitive science and human computer interaction. Pete's a graduate with high honors from University of California at Berkeley and a master's and PhD from UC Santa Barbara. Yeah, we love that Southern California affiliation in the field of cognitive science and emphasis on computational modeling. Pete, thanks again for joining us. I'm going to turn it over to you for what I know will be a super exciting morning.
Thank you very much. I just want to do a quick audio check. Thumbs up, you're hearing me? Great. So I want to thank the Alliance again for giving me this opportunity to get involved with the inaugural SURE program. And I just want to make a quick comment about what we're doing in the region, and I think it aligns perfectly well with the overall ecosystem that the Alliance has been building. So as part of the Army Futures Command, which got stood up a couple years ago, our role as the Army's corporate research laboratory is to operationalize science for transformational overmatch. And so in addition to operationalizing it, we do a lot of disruptive research. We don't do it alone. We do it quite often with academic partners, as well as more and more with industry partners, with technologies like AI in industry outpacing what several academic labs and industry or government are doing. And so I want to make it clear that in the region, although Aero West started about 4 or 5 years ago, we're standing on the shoulders of giants. So I have my esteemed colleagues from the Institute for Creative Technologies, where I've personally been embedded for nearly 11 years. And so with that, I'd like to turn it over to Mr. Kyle McCullough to tell us about the work that he's leading on One World Terrain at the ICT.
Great, thanks, Pete. All right, I'm going to go ahead and start up a screen share here of my slide presentation. As I mentioned earlier, I'm Kyle McCullough. I'm the Director of Modeling and Simulation with the Institute of Creative Technologies. I know we've got Randy and Clark on the line. If either of you want to do a quick overview of the Institute, otherwise I'll run through these slides here as well.
George on.
All right. So yeah, we're a university-affiliated research center. So we're a Department of Defense funded nonprofit organization created in 1999. We are a bridge between the Department of Defense, academia, Hollywood, and the West Coast technology industry. You know, our specialties, what we focus on a lot as a research institute, is basic research, applied research, and advanced prototyping. Some of our areas of expertise are graphics research. We have a vision and graphics lab, VR, AR, and XR. We have a mixed reality lab, virtual humans, artificial intelligence, learning sciences, and simulation and training. So, you know, notably, historically, some things that have come out of ICT is it's where Palmer Luckey created sort of the first iteration of the Oculus. A number of direct work done with Hollywood movie studios for special effects, big game studios, and a lot of the work that we do currently to support the Army's synthetic training environment. And that's what I'm going to talk about today. So we have a program called One World Terrain. It's a multi-partner effort. It's a part of the Army's synthetic training environment, which is a large-scale sort of next-generation training, virtual, live, and constructive training that the Army can begin to take on. And when we started the One World Terrain program, the key focus was that sort of training domain. And very quickly realized that what we were doing with real-world geospecific terrain data actually applied much broader than training. So within defense, obviously operations and mission command, but the simulation fidelity of the data and how it can be applied to existing simulation platforms, newly created simulation platforms, gaming environments, a lot of additional value has come out of that. So we've started to look at the One World Terrain pipeline in sort of a 5-phase operation where you have collection, creation or processing, storage, distribution, and application and runtimes, how you're actually using that data. The goal of what we're trying to do is quite lofty, but you know, creating an authoritative, sub-meter accurate, geospecific 3D data set that can be used for data anywhere on the globe. And being able to create that pipeline so you can easily integrate that data into immersive experiences. A lot to this slide. I'm definitely not going to go through the whole thing. I think the real key of what we've been doing with the program is if you look at creating real world geospecific data, we started in FY 2016, and we're just using a single off-the-shelf drone, running that through just some standard photogrammetric reconstruction software, storing it on a hard drive, and being able to sort of look at that in a 3D model viewer. That's sort of where the program started. And if you look at sort of how we're going across to where we're at today in FY20, the focuses have been increasing the automation of those processes, the accuracy and the interoperability of that data. So it's no longer just drones. It's being able to take data from any existing GIS and terrain data source. So that includes things like Microsoft Bing, Google Earth, satellite databases, commercial and publicly available, as well as existing sort of data structures like OpenStreetMaps, and being able to take all of that data and fuse it into this unified format using automated processes. And so, you know, if you look at the way that terrain data typically exists, and this image here in the top right is out at Catalina Island, the USC Spatial Sciences Institute. And if you're looking at just a typical terrain geometry, you can do some simple analytics. You can measure the heights of buildings. You can visually check to see where roads are. You can sort of measure distances across the ground. You know, there's some very simple and basic analytics that you can very easily do. But what you can't do are more in-depth things. You can't measure the real-time assessment for potential change in the terrain or in the makeup or presence of structures, be it buildings or terrain clutter or vehicles. You can't account for any of the variability in material and object composition. You can't use it for high fidelity analytics or high fidelity simulation. And you can't use it to provide a sufficient ground truth for doing training, whether that be human training or training autonomous systems. And so what we have is a fully automated pipeline that takes that raw terrain data and processes it into something that makes it much more ready for a computer to make sense of and machines to make sense of. So we have a lot of machine learning algorithms that take the source data, understand it, and then output semantically classified data with feature attribution and feature extraction. So some examples of what that pipeline's doing is road attribution and extraction, so that the autonomous systems and simulation environments can now have knowledge of all of the roads, as well as vegetation. Oh, was there a question? All right, sorry. As well as vegetation and ground material identification, so we can actually understand when you look at typical photogrammetric reconstruction of forest, for instance, you're just going to see a mass of trees. So if you try to do pathfinding and navigation through that, it's going to take you around it, because to the computer that just looks like one solid structure. What we do is we understand exactly what those trees are, what the makeup of them is, how many of them are in that area, and we can then replace those using realistic tree models that give us a much better idea for both simulation use, especially things like pathing. Doing the same thing with ground materials, so we have an understanding of what is dirt, what is grass, what is a road, what is a crop field, and being able to take all of that information and feed it into the simulation engine for analysis, as well as to run a higher fidelity simulation experiments. Some of the things that we've done, the bottom left, you know, we're not just doing the exteriors, so we're doing interior and exterior conflation, being able to take all of the available data, fuse it into a singular data set, and use it in these virtual environments. This is just one example of that. And so again, by being able to run this through that pipeline to be able to understand what is the buildings, what is the ground, where are the windows, where are the doors, really feeds the simulation with the information that's going to enable that fidelity for higher quality analytics. Here's an example of just the USC campus running within the HoloLens 2. You know, we're not just creating the data, but we're creating the platforms that enable you to use that data in really interesting and valid ways.
Realistic reconstruction will improve situational awareness and infrastructure protection and planning tasks.
One of the collaborations that we did with the Department of Homeland Security, where we mapped the Rose Bowl going into events at the Rose Bowl, so that they could actually use this to understand security and best practices for actually being able to secure the Rose Bowl for large events. And then this one is just an example of the real world data versus the virtual data, sort of creating this idea of the digital twin, being able to very quickly replicate the real world data with a high degree of fidelity that makes it really useful to simulation and virtual environments. And so by sort of creating this data in a way that makes it incredibly interoperable and sort of coming from agnostic sources, we can take the best available existing data and enable that to be output into a number of runtimes. So whether you want this data to be usable within VR, AR, on a desktop, on a mobile phone, the structure of the data contains all of that information that you might need, and the portability of the data enables it to be rapidly deployed across devices. So, you know, notably, and I think some of the things that I heard earlier during the introductions, that idea of looking at ways from the power grid perspective. One of our our main sort of focus is being able to understand all of the features within a 3D data set, and especially on the defense side, especially when you're looking at things like helicopters, it's really important to know where all the power lines are. So being able to understand a data set and extract power pole and power line information, and be able to both couple that data into a data model that represents all of the information in a smart way to the computer, as well as be able to visualize that in any number of ways once you actually have the 3D terrain data set realized at the end of the pipeline. That's sort of just one example of one of the ways that the data could be applied to support sort of existing use cases that are far beyond the sort of original ideas that the Defense Department intended to be within the training domain. And I think I kept this under time. Any questions?
Thanks, Kyle. So I'll open up with a question, and then as people have them, they can feel free to put them in the chat, or just raise your hand, and we'll call on you. So where are you with integrating sensors that would get an understanding of the electromagnetic spectrum, like given that you're considering power lines and even beyond kind of EM, other types of RF, wireless communications and such?
Sure. So we're sort of looking at that in a few different ways. One is the propagation of RF across the terrain. So being able to use the material attribution data, the actual 3D terrain geometry, and understand how RF would propagate across a real world terrain. And the other piece of that is actually looking at the sensor information to be able to virtualize and replicate sensors, not just RF. We're looking at, LiDAR sensors, ultrasonic sensors, electro-optical sensors, audio sensors. We're looking at ways of being able to actually integrate those into an open platform that can sort of make sense of the environment, utilize that real world data, and then sort of return it in any way that's necessary. So sort of a great example of that is some of the work that we're doing with one of our collaborators at the Office of Naval Research is being able to understand where a radio emitter might be positioned, and without even needing access to the simulation environment, to the terrain, pass in the position just in a standard georeference latitude and longitude, and actually return an image raster layer of that terrain based on the location of the known emitter. So you sort of get out all the information that you need from the simulation system without even having to access sort of all of the, quote unquote bulk that comes with the system itself, all of the terrain data. So looking at ways of being able to utilize things like RF sensors in ways that don't require all of the overhead that would typically come with, a full-scale simulation system for that.
Thanks. Yeah. So a couple questions have to do with kind of capabilities that would lead to this being real time, and then also kind of the detectability of new power lines, for example. If you have a database of terrain and something new is added, how do you do that diff comparison, for example?
Got it. Sure. So there's sort of two pieces to that. I think the sort of the idea of the real-time terrain generation is something that we're constantly looking at. When we first started this, it took about a week to sort of generate a simulation-ready terrain, and now we can turn that around in around between 4 to 6 hours for that same size of terrain. So we're constantly sort of shrinking that. We're both shrinking the time that takes, as well as shrinking the equipment required for that. So what we're actually looking at doing in some of the work that we have coming up is taking and packaging that hardware software combination that does all this automated processing, pushing it into a form factor that can actually fly with the drone, so it becomes a payload on a drone, and then being able to actually begin processing the data as the drone is flying. So, attempting to get closer to real time in the entire reconstruction of a new area. What we have looked at already is change detection. So being able to have processing on board the drone that can actually detect something that is new within the terrain environment and only pass that information back down to the ground for integration. So some great examples of that would be if a vehicle driving through an area that wouldn't have been in the original terrain that someone might need awareness of. So that information could be passed back directly based on the knowledge of the existing terrain area. For that idea of sort of updating existing information. So if we for instance had access to a database that had new information about sort of any feature locations, it's really easy to then have only that part be part of that data fusion process, so that the terrain gets sort of, I won't say instantly updated, but very rapidly updated from the knowledge coming from that existing database. So much in the same way that the redoing the overflight would work, but being able to just pull that from an existing database.
Great. So thank you so much for that brief yet very compelling presentation. So we'll keep the questions going. Hopefully you can hang out and get to them in chat. But we'll switch to our next presenter. Sang-Kai Chang from UCLA is going to talk about simultaneous localization and mapping, an algorithm based on online EM. So looking forward to this talk. Thank you.
Hi, everyone. Let me share my screen first. Okay, can anyone see my screen? Nice, cool. So my name is Sang-Kai. I'm a PhD student from UCLA. And okay, so my research focuses on simultaneous localization and mapping, or simply SLAM. So whenever we need a technology to interact with the real world, and SLAM is essential to establish the relationship between the environment and the device itself. So therefore, it is used in a lot of applications, including like AR and autonomous driving. And let's take a look at the SLAM system here. So we can think of SLAM as take the input of images and like IMUs and output some estimation of the trajectory and the environment that we just call it landmark. And recently, there are a lot of improvement in SLAM, but basically in the front end with a lot of different computer vision innovations. At the same time, the backend remains pretty typical. And I have some ideas, some new ideas on how we can rethink about the SLAM backend. So commonly, the SLAM backend is solved as an optimization problem. And the optimization problem is a batch or offline algorithms, which means that this optimization will grow bigger and bigger, as you can see from the figure, that you need to process more and more data as time goes by. So a significant computational power is expected in the end of the process. Even though there's some heuristic way to bring down this cost, the fundamental solution is still pretty open. Instead, our approach is an online algorithm, which means that only the most recent data needs to process. As you can see from the figure here, only the most recent data is processed. And in other words, our approach can discard historical data along the way while maintaining the optimality. This page shows the theory behind it. So this is the typical solution of SLAM. So in our solution, first of all, we model the SLAM as a hidden Markov model and solve it by the EM algorithm. And according to this paper, that you're able to solve the hidden Markov structure in an online fashion, which can bring down the cost of the SLAM. So in a very short presentation, in summary that while SLAM backend is computationally expensive, our approach provides an efficient solution for the SLAM backend, which is especially beneficial for power-limited applications. Thank you so much.
Thank you. I think you got us back on time. So I know I have some colleagues from ARL. I'm pointing to you, Dr. Suya Yu, who have a deep expertise in this. But my general question is, you left off your presentation talking about the algorithm. Where are you, or where is the field in being able to kind of take what you've done in developing this new algorithm and proving it in some type of prototype system to see if there are any kind of real world experimental considerations that where you may need to introduce new parameters or other constraints to your algorithm?
Yeah, thanks for asking. So currently that we only have the theory behind it, and we're going to test our real system. And the most exciting system that we're testing now is actually a system just with IMU and monocular camera. So this is the most limited case that we can think of. And however, it also provides the essential, it pretty much provides the sufficient information to enable a SLAM system. And especially that since our innovation is on the backend side, so we can pretty much leverage whatever front end we're using. For example, different kind of feature extraction, different matching, feature matching algorithm. I think they will pretty much remain the same or remain intact. And while we can process this information and put it into backend, then that's where our algorithm makes a difference.
Great. Are there any other questions from the group to Sankai? So Andy Wilson's asking, so is the primary benefit a speed trade-off or computational efficiency, or speed and computational efficiency? And if so, what are kind of the order of magnitudes that you expect based on the AEM algorithm?
Sure, that I just see the question. So first of all, I don't think this algorithm can provide better performance. The performance is pretty much limited by the optimization problem that you can solve. So yes, this algorithm is aiming to bring down the cost. And what's the other question? Like,
so when you say bring down the cost, I guess the follow-on question is kind of what order of magnitude, and I guess for my case, what relative cost are you talking about?
Okay, so we did some analysis on the some theoretical computational cost analysis. So if we think about just pure optimization base, the data that you have to process just grows linear with time, like the longer time that it grows. And however, in our approach, that seems we process each block. And even though the block size grows, the block size only grows like exponentially. So the entire data that you need to process grow only logarithmically along the time, rather than linearly with time. Okay, someone asked about the location accuracy with this approach. So theoretically, we test on some very simple system. It doesn't really affect the accuracy because there's a proof behind it that it says that, yes, you can discard this data and without affecting the accuracy. But we're still testing on the real system. But there are some slightly details in here. So actually, they're not discarding data. They store the data in their landmark estimation. So they keep updating their landmark estimation. However, they don't need the historical trajectory information. That's the somehow like when we separate into the EM algorithm, one part solves the E step solves the trajectory, M step solves the landmark. So we can keep the landmark while you discard the trajectory, which brings down the cost.
Any other questions from the group? One I was thinking about is if you're able to improve like depth inference from the monocular image that you're getting.
So that's a very interesting question. I would love to answer this way. So even though this is a method from the back end, and when you talk about the depth estimation, it's actually done in the front end. Like we have several images and we try to estimate the landmark. So that's the next stage of research. I'm still pretty open and pretty excited about this. But actually, if we know that our backend can be solved really efficient. How can we change the entire architecture of the SLAM system? Definitely, there's some way that we can improve the front end as well, especially like depth estimation, and also like a lot of SLAM EM algorithm is also used in other part of the SLAM system. For example, the feature correspondence problem. So I think there's a better way that if we know that we can have a better backend system, then we can rethink the entire architecture of the SLAM system.
Yeah, thank you for that well thought out answer. So I see Suya posted a question in the chat, so hopefully you can take a look at it there. But at this point, we're going to move on to our next presenter. It's my pleasure to introduce Professor Josie Chen from University of California, Riverside.
Great. Hello, everyone. Thank you very much for having me here. Let me just open up my slides. All right, here we go. Hope you guys can see my screen now. So I'm Josie Chen. I'm an assistant professor at UC Riverside in the computer science department. I work on multi-user AR software platforms. So what do I mean by this? What I first want to say is that social multi-user AR is coming up in the next wave of AR apps. So, you know, Pokemon Go is the big example of AR, but now Pokemon Go is releasing multi-user features where you could have like multiple people, there's 2 people here, looking at a common view of a bunch of Pokemon in the scene. Or you can play virtual tic-tac-toe or virtual graffiti in Google's Just Align app. Or even Minecraft has released like a AR Minecraft, and you have multiple people here that are interacting with the same holograms. So the main thing I want you to know from this is that there are multiple people who are interacting with a common set of holograms. And that's basically what I focus on. Well, is it all just fun and games? Most of the examples we see nowadays in practice are like, Pokemon Go and like fun stuff like that. But you could also imagine multi-user AR just being more useful for more practical stuff. So imagine you in a first responder scenario, you could have like firefighters equipped with AR, and they could all be helping each other and looking at a common set of virtual objects or holograms and sort of interacting with the scene and so on. Or like someone was mentioning utility repairs. You could have multiple people that are equipped with AR glasses, and they could be collaboratively repairing something and seeing things on their AR display in real time. So that's kind of the general problem space I work on. And what I want to tell you about is what's currently lacking from multi-user AR. So I'm going to try to show you a video. I know it's a little bit risky. Hopefully it works. So let me share my video. Video is always a tough one these days. Okay, let me cue it up. All right, so what you're going to see in this video is 2 smartphones that are going to be doing a multi-user AR app. And I guess the main thing I want you to see is that it's really slow. All right, so there'll be a lot of awkward silences. So let me play the video. So first what's happening is this phone is downloading a large app in the background. So it's producing a lot of background traffic over the mobile network. And here you see 2 phones, and they want to see the common set of holograms. So what you're going to see is that things that are on one phone take a long time to load, and it takes a long on the second phone as well. So here the first phone placed this little anchor thing, and it takes some time for it to show up on the second phone. Now the user is making a gesture to create a virtual deer, and you see this gesture is detected. The virtual deer appears on both phones. Now the user is creating a virtual dragon. This is a very lightweight, small dragon model, so it should also be pretty quick. So you'll see it appears on both phones. But next, the user is going to create this really large dragon model that's really high quality and has high fidelity, so like a lot of like meshes. So now you can see the gesture has been detected, but we're basically waiting here. We're stuck. Nothing is appearing because the data is taking a long time to transfer over the network and share between the 2 AR phones. So we're waiting. Nothing is appearing. And let's see. So finally, the dragon model appears on the first phone, and it appeared on the second phone as well. So that's all I wanted you to see here. And let's go back to the slides. So the main takeaway from that is that it takes, when we measured it, it took 28 seconds for the dragon to show up on, the virtual dragon to show up on the first phone and the second phone. And that's because all of this data communications that's happening over the mobile network. It's because of all this computation that's happening in the background. And it's kind of a poor user experience, right? No one's gonna use these Pokemon Go multi-user apps if like it takes 30 seconds for the Pokemons to appear. All right, so that's one challenge. We did some measurements of why this is happening. So this is a collaboration that we did with AT&T, where we measured what are the bottlenecks of this slow performance. And basically we find out that the communication is about 50% of the latency, and the computation contributes about 30% to the latency in the kind of example, that video that I just showed you. So a second major problem that we find is that battery is a huge drain for mobile AR. So here in this plot, I don't want to show you too many plots, sorry, but I don't, a lot of our work has, unfortunately, the results, it's like in plots, not in pretty pictures. But what I want to tell you is that AR kind of SLAM operation consumes just as much power as, say, like a deep learning, which we all know to be pretty computationally intensive. So if you look at the battery drain of a phone running SLAM versus a battery drain of something running deep learning, they basically drain a lot of battery. So after 1 hour, you've almost lost 50% of your mobile device's battery. So you can see this also being a big impact on user experience. People aren't going to want to use mobile AR apps if the phone gets super hot and the battery drains out really quickly. So I just spent a bunch of time motivating the kind of problems that we focus on through real measurements. So what is my research about and my group's research? What I work on is the fundamental AR platform to support multi-user AR. And we focus on making things low latency and also lowering the battery usage. So probably in contrast to some of the other projects you're going to see today, we don't do a lot of like graphics rendering and like pretty pictures and stuff. It's more about making this fundamental AR platform that's fast and energy efficient, which makes it easier for the user to use. And then you can build all these like cool graphics and engines on top of that. All right, so I will just like really briefly overview some of our results. So our one project we worked on is about low latency, improving the communication efficiency. And what we basically do is we adapt the uploaded AR data to the environment. So we basically make the AR app really thrifty and only uploads data that's really needed. So again, I'm just going to skip all the details here, but what we did is we compared our prototype, which is on a mobile phone, compared to Google AR Core, which is a mobile platform for AR developed by Google, runs on Android phones. So we find that in the certain scenarios that we studied, we can save about 50% latency compared to AR Core. So instead of having 30-second time delay for the dragon to appear, you can have 15 seconds. So we're not quite at real time yet, but that's where we're trying to go. One note that question that people often have is 5G going to solve all the problems for AR communications? My answer to that is no. AR is mostly upload data, so 5G focuses a lot on the download speed. AR computations are also a significant bottleneck in latency, and also AR apps themselves are not very clever in how they use the network. They just upload enormous point clouds. It's kind of a waste of bandwidth, and it contributes to user latency. But I know that was really fast. We can always discuss later. A second aspect we also work on is making the computations faster by running them closer to the device. So running it on the device itself can be really slow. Running on the cloud incurs a long latency to transmit the data to the cloud and back. And running on the edge can be a lot faster. So I have some examples here. I guess I'll show you really quick. Let me try to share. So here's the first one. So here is if we don't have this optimized solution, we're just scanning around my office and there's supposed to be annotations appearing, but you can see the annotations appear very slowly, or they're kind of mislabeled, they're kind of drifting across in time. Nothing's really popping up, right? So this is an example of an unoptimized solution. And if we change to something that's more optimized, let me open it up. Here we go. If you change something that's more optimized, you have all of these annotations and stuff popping up really rapidly. That's because the computations are running much more quickly on the edge networks, so it's a lot faster. Okay, and I'm just gonna wrap up now because I think Pete is giving me the evil eye. No, I'm kidding. So our last project I want to talk about is reducing energy drain. So again, here we try to optimize how often AR computations run based on the characteristics of the scene. And the take-home message, I'm going to skip all the details. The take-home message is that we can extend the battery life by almost 2 times compared to just some default type approaches. So just to summarize, what I've done is I want to tell you that multi-user AR is coming. You have all these commercial apps that have multiple users and interacting with this common set of holograms. What my group has found is that there are significant latency and battery issues associated with multi-user AR. And we basically try to find solutions to solve these problems. We do experiments on mobile devices mainly right now, and we can find pretty significant speed ups and battery improvements using our techniques. All right, so I'll stop talking now. And happy to discuss.
Thanks, Josie. This is great. We we probably don't have as much time for too many questions, but my thoughts were along the lines of what Andy posted. So he's asking, how might this get packaged for commercialization, and who would be likely target customers?
So what we've developed now are like optimizations to the fundamental AR platform. So we mostly work with like open source systems. So this is something that you would want to see incorporated into an AR platform. So like Google AR Core or Apple AR Kit are also, you know, commercial AR platforms. So you want to see this kind of technology being incorporated into those platforms.
And as a quick follow on, what could the ecosystem do to kind of help operationalize your most recent papers into something that's integrated within one of these platforms?
So most of what we need is from the platform side of things, but you could also think of the AR app, like AR developers themselves also making modifications to how they use the network or how often they call AR computations. So we'd imagine this as we would develop like a set of API, like a software thing. We develop a set of APIs and we tell developers, hey, use these APIs and this will automatically make your app like faster or you know, use less battery. So yeah, set of APIs is the shorthand answer.
Great. So yeah, encourage people as they are already to continue sending kudos and any other potential questions for Josie. And so thanks for taking the time to do this. And with that, we'll switch back to the UC within metropolitan LA. It's my pleasure to introduce Professor Jacob Rosen from UCLA. We'll be talking about VR tasks for stroke rehabilitation.
Hi, and let me share my screen. Can you see that? Okay. So I was involved in a stroke rehab for all of my career, but I'm by training an engineer. So I will present the engineering, an engineering solution to stroke rehab. I've worked all of my life with clinicians, but that is my background. This is Lisa, by the way. She's on the call. You don't see her face, but this is this is how she looks like. And we missed an opportunity with COVID in a sense of getting the right PR. She was on The Economist in an ad. But COVID presented actually an opportunity that I'll go back to it later as far as how this solution can actually help in that context. I want to give you some framework. I know that some of you are working in stroke and rehab, so I believe that medicine is going through a revolution right now. It's equivalent to what the industrial revolution was. The world was going through industrial revolution, and what are common to both is automation. Automating healthcare is essentially what we will experience in the near future, and it's probably the only way to gap between the requirements and the cost, and the gap between clinics and homes. So the leading idea behind this whole concept is to deliver healthcare in the home setting, and to give the patient the control over their recovery. Before I go further, I want to show you two videos. All time. Just a second. Or maybe I'll show it at the end. But I have two videos to show that concept. But the product has essentially 15 different sensors on the body. We also have a hand right now, so two hands. We are tracking the body in a three-dimensional space, and the patient is essentially playing a game against an entity. This entity is not passive. It's an AI entity that is evolving as the patient is recovering.
Jacob, your slides aren't showing, by the way.
Oh, sorry. Let me share again. Well, since I'm showing, let me show you the two videos. This is how it looks like. During therapy, this is, by the way, a postdoc. Is not disabled, but we have about 18 different games, and the patient is playing with these games, and they evolve as the patient is improving their motor skills. I want to show you another video that will represent the glove. So in addition, we have gloves, and this is a virtual representation of playing a piano. And we have 5 fingers. All the fingers are tracked, and all the digits of actually every finger is being tracked. So it's a very high fidelity system. Let me go back to my slides. Can you see them?
Yes, yes.
Okay. So I missed the first part, so I don't know what was presented. I may repeat myself, but there are 23 million people suffering from physical disability. And this is how the market is valued from the investment perspective. Outpatient treatment is about $30 million. It's broken down to services and equipment. This is a pie chart that's showing all the physical disability out there. We decided to start with neurological, in particular stroke. The reason why this is attractive is because it's a process that takes a lifetime to some extent to recover. So it's not something that if you had a procedure, you come for a few weeks, you recover, and the therapist will never see you again. So stroke in particular, there are 7 million people suffering from stroke right now, and every year about 800,000 would add to that number. Just to give you a timely perspective, every 45 seconds, someone in the US will experience stroke. So who are taking care of them? There are 22,000 facilities, and you can see the breakdown of these facilities providing care for these individuals. So what's the problem? The problem is that standard therapy failed. It failed miserably. Some will not admit it, but in closed doors, they will say that we don't know what we're doing and we don't even know what to do to improve that. So the result of this statement is about 63% of all the stroke patients will remain with permanent disability. Some of the recovery related to, so you know, in stroke, half of the body is paralyzed. People will recover gait, but 85% of all the cases will remain with disability of the arms and the hands. The challenge is that the current therapy is providing stroke patients about 3 months of paid therapy. This is compared to about 18 years of developing motor skills when we are growing up. So stroke would essentially bring us to some extent to a baby level in terms of our motor control, and 3 months is simply not enough. And in these 3 months, only 12 hours of face-to-face with therapy, this is what we get. The second problem is that the entire therapy is therapy-centered, meaning you get as much therapy as the therapist would have time for you. And this is obviously not the right way to go. So the idea is to shift the paradigm from a therapy center to a patient center, and to shift the treatment from a clinic to the home. So the product would have both software and hardware. You've seen the hardware. The software will have about 18 different games. We'll collect data online. There is an agent that will personalize the therapy. There will be an automatic diagnostic and assessment tool built in, and there will be a web connectivity built into the product. This is just a schematic of all the games. They are based on classical games that, to some extent, people have shown addiction to playing already. So we are not reinventing the wheel in that case. I will not go too much into the science, but the scientific foundation of all the therapy is brain plasticity. We are also using dual arm manipulation, and we provide intellectual engagement, so the therapy is more interesting to the patient. The other element is we're personalizing the therapy through an AI agent that will change the game. So go to the market approach. We view 2 routes to the market. We view the therapy centers as the middleman between the company and the patient. The patient will come to get their regular therapy mandated by their primary care and provided by their insurance, but as part of that process, they will be presented with the product, and it's something that we'll take home during these first 3 months, and overall we'll continue with this therapy following these 3 months of paid therapy. The other options is to address nursing homes. There are many disabilities, both physical and neurological, in this market, so that can be another route to use the product. There are 3 elements in this scenario: the patient, the outpatient clinics, and the healthcare insurance. The product is making sure that everyone is happy. From the patient perspective, we increase the dosage, we provide a lifelong follow-up. From the outpatient clinics, we provide them a continuing therapy over the course much longer than 3 months. We provide them an increased source of income. From the insurance companies, we reduce cost, and we build a significant database that they can use eventually to direct payment and strategies.
Jacob, I see you're on slide 30 of 55.
Yes, well, there are more slides. There
Yeah.
are more slides in my presentation that I'm going to
Yeah.
present. So I'll
If you
stop at one point.
Okay,
But
if you
if
could
you
just
want me
wrap
to
up in
stop-
the next minute, that'd be great.
Okay, well, I'll just go quickly to the finances. We did a very detailed analysis here. In year 5, we will be profitable. We are seeking 2 rounds of investment, $3 million each in a 5-year period. The team as it is right now include Lisa as the CEO, I'll be the CTO, and we have a very experienced chairman who was a Fortune 500 CEO. And that's it. So I would like Lisa to add more to that. She has comments about community, and since she experienced some stroke case recently in our family.
Hi, I know I have very little time, so I'll make it really quick. The one aspect that I'm extremely passionate about, feature that we've been working on too, is to have a community of the users that actually can interact with each other. And what we have found previously with stroke is that it's a very isolating, depressing state of mind, and then we add COVID, which has certainly augmented that situation. So we are working to develop a community where people can talk to each other, compete against each other, because games is, that's how it's fun. We'll keep them engaged. But I did want to add that, and I know we have very little time, so thanks so much. I'll end it there.
Yeah, thanks for adding that. And I guess one comment or question is where you are in the commercialization process. I see you're raising an initial round. Kind of how far are you in attracting investors or productizing this?
So I'm working with Bruce Dapkin from UCLA. Some of you may know him. We are starting a small clinical evaluation with 12 subjects. We have about 15 systems right now in my lab. This was at least explained to me a necessary step to even approach investors, to show them that someone is actually using that. It's not just an idea in my lab or in my mind. So I think following this positive response to that, we will also gain clinical input from clinicians using it and end user input, and we'll be in a better position to start pitching it to the investment community.
Thank you. I'll follow on with some other questions in the chat. But thank you again for presenting this. And at this point, we'll move along to Steve from Nano AI. Steve, please share your screen.
Cool, thank you. Yeah, let me go ahead and get that started here. Perfect. Can you see that?
Yes.
Yep.
I got it.
Okay,
Yep.
okay. Great. Yeah, so I'm Steve McCloskey. I'm the CEO of Nanome. Yeah, this is our product that you see there. We're actually creating virtual reality software for nanoscale design. So a little bit of background about how we got here. I'm actually an alumni from UC San Diego. I studied nano engineering, just kind of like a combo of what you see over there with the gold nanocube and the protein. It's like everything at the nanoscale. So as a nano engineer, I always wanted to get hands-on. So how do you get hands-on with things that are made out of atoms? You can look at them with microscopes. You could kind of like adjust some things, do some bottom-up synthesis, but you can't get hands-on. And so I looked at virtual reality as a way to allow me to zoom down to the nanoscale and start building with my atoms and molecules. And through ICOR, a bunch of other customer discovery, we found a really great market need in pharmaceuticals and biotech. And although pharmaceutical and biotech industry is super into three-dimensional technology. They've been into it in the 80s, the 90s, the 2000s, the teens. Really, they've been looking at proteins on sort of every VR system imaginable, from caves and silicon graphics up until modern head-mounted displays. And where we come in is building the nanoscale design home for science. So this concept is kind of simple. You start from the atoms and you work your way up. And you have a VR system that could allow you to manipulate all the atoms, hook up with simulations, and start designing things from drugs to new materials and new technologies. So a little bit of traction that we have here. So in 2017, we started working with Novartis. This is actually from a paper that we co-authored with them last year, showing the collaborative drug development process. So in this, you have multiple structural biologists, multiple chemists. They're all kind of getting together, working together, and instead of looking at these things on a two-dimensional screen, they're getting into the binding pocket, and it's like designing a key for a lock while you could zoom into the lock and stand inside of it, understand every single little piece of that lock in great detail so you could design the best key. It's much more complicated than that in terms of all the quantum interactions going on at the nanoscale, but that's kind of the simplified overview of how to make drugs using structure-based drug design. So here you can see a little bit of a GIF with two people just literally inside the binding pocket looking at it. All these data sets are parsed in. So this is a text file of a bunch of atomic coordinates of like carbons, nitrogens, oxygens. We take that data and we generate the model that you see here. So we don't pre-compute like video game object models. Every scientist has different proteins, different data sets. Some of them are highly proprietary and we don't even see them, but our software could still handle them. So really getting them the information they need, whether it's PDFs, documents, different types of data, or really the structural data of the proteins and molecules. We try to really make this a home for all the scientists. A little bit of what we're doing with COVID-19. Obviously, the pandemic has affected everyone. Back in January, we were pretty sussed out by everything going on in Wuhan. And we said, hey, who around the world is looking at this? There weren't many people in January looking at it. But we actually found in Australia in the National Research Lab, Data 61 Cicero, that there were people that were using Nanome to look at the proteins associated with SARS-CoV-2. And what we did is we had some international collaborations with them. And they recently published a paper in Nature showing the mutations that have occurred on the spike since the start of the outbreak in China, all the way up to where it's gone till now. And basically showing where the vaccine efficacy would be. And they referenced our software and actually created a workspace, which is like a file that we create that's like all the proteins, all the colorings, all everything, all saved. So they made like the first pre-made workspace published with the paper, and it's in Nature. So that's been awesome. We're working with other companies. Ensoka Medicine are using AI to generate molecules. We use VR to analyze them, spit them back to the AI, make them better. It's a nice like human in the loop AI system right there. And then Jumpe Pharmaceuticals and Escalate for Cove in Italy, they're using supercomputers to screen. So they've been doing a lot of drug repurposing there, a lot of checking if antibodies are going to work for the MINC mutations. That was another one we were just working with them on too. So it's really awesome to help the global scientific front to fight against COVID-19 and hopefully cure this thing. And just a little bit on the computational aspect. So, this is our software right here, and we try to make it super intuitive for the users to be able to, reach out, grab, design things, kind of do everything pretty intuitively. What you see going on in the background on the menus is actually our Python-based API. And so that allows you to connect with complex backend computational chemistry type software that typically an average chemist that doesn't know much about computers wouldn't really have ready access to these types of things. And so it's a huge industry push to try to get more advanced computational simulations in the hands of non-expert users, people that are experts in chemistry and benchtop chemistry, but not experts in command line software usage. And so what you see here is every time you change a molecule, that data goes to a program that calculates chemical properties and then displays them to the users alongside a 2D snapshot. And chemists think in 2D, although we're VR and building these things in 3D, they still want to see it in 2D. I know it sounds weird, but it's very true, and it's part of the workflow for them to see it in both 2D and the real three-dimensional VR aspect. Cool. So just a little overview here. So collaborative VR. This isn't just single user VR. Single user looking at a protein, designing things better. Of course, there's a lot of benefit. Everybody working from home, to fight COVID-19 during the pandemic, that's awesome. That's the type of stuff that we love and want to encourage. You could get better ideas by looking at these things in the full 3 dimensions, faster understanding because you could just see it right in front of you and understand that complicated ball of spaghetti. Presentations right now, people basically use PowerPoint just like this, but they basically do VR presentations now for the companies that have VR, and that leads to a lot more effective design meetings, especially when it's multiple sites. Some companies have a site in Boston, a site in San Diego, a site over in Europe, and getting these teams connected and working around the world has been super validating that virtual reality really is the technology that everybody is going to be using for these types of complicated 3-dimensional design problems. Yeah, and so just question for the audience, what do you all see the future of spatial computing for science? We've all seen Iron Man, hopefully, and the periodic table, and you're dragging stuff and you're making things. That's reality at this point. It's this is what we do. We work with over a third of the top 15 pharma companies, a ton of biotechs, hundreds of universities. That's our current traction. Our business has been around for about 5 years. And we really want to change the way people do science. So it doesn't matter if they're at a university, if they're at a private company, if they're a high school kid. We want the future gen to all be these superpower AI computational users by just kind of intuitively grabbing things and doing things in VR. So yeah, that's where we're at. Thanks everybody for listening, and I'll be happy to take any questions.
Yeah, this is great. So we got a question from Andy Wilson on whether there's a community or open source aspect about this, and it's what I was thinking too. When I saw this, I immediately thought of kind of the folded realm of stuff from UW and how they've gamified protein engineering. And so yeah, I think it also speaks to Andy's thoughts.
Yeah, well, there's definitely the folded type of everybody working together and crowdsourcing aspect to it. We actually wanted to crowdsource the development of small molecules, and it looks like we talked with some grad students that were previously with the UW HIT Lab, and they actually did not do that due to the intellectual property concerns. So we pretty much built and launched an entire Ethereum mainnet decentralized application on the blockchain in order to tackle that specific issue of who created what first, in order to help facilitate a crowdsourced chemical design competition. So basically you design it, you hash it on the blockchain, it's there forever giving you provenance and original authorship, whether or not you want to disclose it at that point. So yeah, we'll see how that plays out on the legal course. On the other side of things, the open source community aspect. So that slide that I showed with the chemical being built and then all the properties, that's actually an open source piece of software that calculates those chemical properties. This one in particular is called RDKit. It's running on a server. The user is interacting with that server and getting the data between them. But we could see a huge open source community on all these plugins. So open source scientific software stack, we believe that all the backend quantum physics calculations, all that should be open source, auditable, verifiable. And even the plugin scripts that we make to help connect those softwares with our platform, we're open sourcing those and creating an open source community around that.
Any other questions? If not, I have a tons, because this relates to my background in medical visualization and spatial cognition. So when you were showing the different projections, I think it was a Fisher projection. Like, have you compared dash wedge versus Fisher projections, or is it a feature that people can toggle? Because that's some work out of a lab that I used to work in. They were just comparing how people build 3D representations from these preferred or indoctrinated ways of teaching chemistry.
Yeah, I think it's a great point. Yeah, the method that we've been going with is like provide the users with several different options. So, you know, when they go in there, they could, of course, you know, change around the atomic representations everywhere from like line and stick models to ball and stick to like Van der Waals view. Yeah, even the ribbons that people have the cartoon alpha helice, beta sheet type of model. You know, changing that around to what they like, even different types of surfaces. And I'd say the surfaces are probably one of the most important nuance, because you could have a cartoon ribbon, you could have a cartoon whatever, and so long as the atoms are in the right places, you know you're doing good. But the surface is something that gets very nuanced in terms of like, is it the solvent accessible surface? Is it the solvent excluded surface? Is this some type of hybrid surface that gives you other data? You know, there's a whole water map aspect to this as well, with where all the waters are located and sort of visualizing that, because the waters are a part of the protein. So there's structural waters and a lot of peripheral waters that are super important. And so even having that in there and having clever ways to visualize that. So we continue adding more views, and you know, anytime a user wants to have a view and thing that we don't have, we have to reevaluate if we should add that. So far, we've just been adding that in and making it a user option to toggle it around.
Yeah, thanks for that response. I posted a link to some work happening at ARL West with other collaborators, and yeah, would love to stay engaged in how you ponder about the future of spatial computing. So with that, I'll turn over to the Alliance colleagues to close this out.
Thank you, Pete. I want to first shout out to everybody and say, awesome. Thank you so much for being a part of our inaugural program. Thank you to Pete for being an amazing moderator and getting some great discussion going. A true shout out to our presenters, Kyle, Senkai, Josie, Steve, and Jacob. You guys were awesome. I will be following up with everybody. I'll send along emails on the agenda that I sent out. Links to their programs or to their websites are on the PDF, so please feel free to utilize that. We thank you so much for giving us an hour and a half of your time this morning. I am super pleased to say that we are ending right on time. Super unusual for events like this, but thanks for your participation. Thanks for being a part of this. We are planning on hosting many of these in the future, and we would love for you to be a part of it. So if you have extra questions that you'd like to ask, please, my email is also on the agenda. Feel free to reach out to me. My cell phone's on there as well. And Andy, if there's anything else that you'd like to say before we end, I'll shoot it over to you. Otherwise, we can let everybody have a wonderful Tuesday and a great week. And I will preemptively say happy Thanksgiving next week.
Yeah, thanks again. Just to echo, love the incredible work that's going on in Southern California. Makes my job a lot easier to be a booster for people like yourselves who are foraging at the frontier of innovation. And that work is only as impactful as we get people who can see commercial applications to partner with you, support you. So we're really hopeful that this series of kind of virtual engagement will kind of once again help all of you reach the full potential of the work you're doing. So thanks again, and have a wonderful Thanksgiving coming up, and be safe and solve some of the world's most important problems. With that, thank you.